Have you ever looked up at the night sky and felt impossibly small? There's something humbling about standing under that vast cosmic canvas, knowing that every pinpoint of light tells a story billions of years in the making. But what if I told you that you're more connected to those distant stars than you could ever imagine? In your body, right now, are atoms that were forged in the hearts of dying stars. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of your DNA. All these elements were created in stellar furnaces that burned bright and fierce before Earth even existed. When we look up at the stars, we're not just observers of the cosmos. We are its children, made from star stuff scattered across space and time. But our connection to the universe goes deeper still. Every breath you take contains atoms that have existed since the dawn of time, 13.8 billion years ago, when everything we know burst into existence in a moment we call the Big Bang. The air around you, the ground beneath your feet, even the screen you might be watching this on all trace their origins back to that singular moment when space, time, and matter were born. Tonight, we're going to take a journey together. We'll travel from the familiar comfort of our solar system to the edge of the observable universe. We'll watch stars being born in vast cosmic clouds and see them die in spectacular explosions that seed space with the building blocks of future worlds. We'll explore black holes that bend the very fabric of reality, and we'll contemplate the mysterious dark matter that holds our galaxy together. Along the way, we'll uncover some of the most profound discoveries humanity has ever made. We'll learn why the stars shine different colors, how light takes millions of years to reach us from distant galaxies, and why Earth's perfect position in space makes it an oasis for life. These aren't just abstract concepts. They're keys to understanding our place in the cosmos. As you settle in for this astronomical journey, remember that you're not just learning about the universe, you're learning about yourself. Every scientific discovery we discuss, every cosmic phenomenon we explore, helps explain how we came to be here on this pale blue dot, contemplating the stars that gave us birth. So relax, look up, and prepare to see the night sky with new eyes. Because once you understand the cosmic story written in starlight, you'll never look at the universe the same way again. Our first stop on this celestial tour is understanding the very stuff that makes us who we are and why we can truthfully say that we are all made of stardust. Look at your hand for a moment. The carbon in your skin, the calcium in your bones, the iron carrying oxygen through your blood. All of these elements have an incredible origin story that begins in the hearts of ancient stars. When we say we are made of star stuff, this isn't poetry or metaphor. It's a scientific fact that tells the story of our cosmic heritage. Let's travel back to the very beginning, 13 billion years ago, when our universe emerged from the Big Bang. In those first moments, only the simplest and lightest elements existed, hydrogen and helium, with trace amounts of lithium. These elements alone couldn't build something as complex as a human being. For that, we needed stars. The first generation of stars formed as clouds of this primordial hydrogen and helium drew together under gravity. These weren't just ordinary stars. They were monsters, more than 50 times the size of our sun. Inside these cosmic giants, tremendous pressure and heat triggered nuclear fusion. the process that powers all stars. This is where the universal assembly line of elements began. Through nucleosynthesis, these first stars forged heavier elements from lighter ones. Deep in their cores, hydrogen atoms fused to form helium. Helium fused to form carbon, and the process continued, creating progressively heavier elements. But these first stars couldn't create everything we see today. They were just the beginning of a much longer story. When these massive first-generation stars exhausted their fuel, they died in spectacular explosions called supernovas. These explosions were so powerful they scattered the newly created elements across space. Think about that for a moment. The death of these stars wasn't an ending but a beginning. Their remnants became the building blocks for the next generation of stars. This next generation of stars, seeded with these new elements, could produce even more varieties of matter. Every element up to iron can be forged in the heart of a star through nuclear fusion. But the heaviest elements, everything beyond iron, required something even more dramatic. They could only be created in the extreme conditions of a supernova explosion. This process of stellar death and rebirth, what scientists call galactic chemical evolution, has been occurring for billions of years. Each generation of stars enriches space with more elements, creating a cosmic recipe book that grows more complex over time. When we look at a periodic table, we're really looking at a stellar family tree, showing us which elements came from which kinds of stellar processes. The numbers tell a remarkable story. Oxygen, which makes up 65% of your body by weight, was forged in stars more massive than our Sun. The carbon that forms the backbone of every organic molecule in your cells was created by stars 3 to 8 times more massive than our Sun. The calcium in your bones, the phosphorus in your DNA, the iron in your blood, all of these elements were manufactured in stellar furnaces and scattered across space in tremendous explosions. But how do we know this is true? Scientists have found proof in the form of pre-solar grains, tiny specks of stardust that are older than our solar system. These microscopic time capsules, found in primitive meteorites, are incredibly rare and precious. Each grain is just a few microns wide, 100 times smaller than the width of a human hair. Yet they carry within them the signature of the stars that created them. Our own solar system formed about 4.5 billion years ago from a cloud of gas and dust that contained all these stellar-produced elements. This means the atoms in your body have existed for billions of years. They've been part of stars, part of the vast clouds between stars, and now they're part of you. When you breathe, you're inhaling atoms that have existed since nearly the beginning of time. The process continues today. Stars across our galaxy are still forging new elements and ending their lives in supernovas. The spectacular Veil Nebula, which stretches 110 light-years across, is the remnant of a massive star that exploded about 8,000 years ago. When we look at it through telescopes, we can actually see different elements glowing in different colors. Oxygen glows blue, hydrogen appears red, and sulfur shines in green. This continuous cycle of stellar birth, death, and rebirth means that everything on Earth, including every atom in your body, has a cosmic origin story. The only exceptions are the hydrogen atoms in your body, which make up about 9.5% of your mass, and trace amounts of lithium. These elements are truly ancient, dating back to the Big Bang itself. Understanding that we are made of star stuff gives us a profound connection to the cosmos. Every time you look up at the night sky, you're seeing the factories that created the elements that make up your body. Those twinkling points of light aren't just distant suns. They're the ancestors of every atom in your bones, your blood, and your brain. When we study the stars, we're studying our own origins. The same processes that created the elements in our bodies are still at work today, visible in the nebulae where new stars are being born and in the spectacular explosions of supernovas. We are, quite literally, children of the stars, carrying within us the legacy of cosmic processes that have been ongoing for billions of years. Now that we understand how the elements in our bodies were forged in the hearts of stars, let's journey even further back in time to the very moment when everything began. 13.8 billion years ago, something extraordinary happened. The entire universe, all of space, time, and matter, emerged from a single point we call the singularity. This moment, which we now call the Big Bang, wasn't an explosion in space. It was an expansion of space itself. Everything we know, from the countless galaxies to the atoms in your coffee cup, began in this singular moment. But to truly understand this cosmic birth, we need to examine what happened in those first crucial moments. The universe began in a state of incredible density and heat. Modern cosmology tells us that in less than a second after the Big Bang, something remarkable occurred. This period, known as cosmic inflation, saw the universe undergo an exponential expansion. During this brief but crucial moment, the universe grew faster than the speed of light, stretching space itself in all directions. This early inflation period helps explain several mysteries about our universe. For instance, have you ever wondered why the temperature of space is so remarkably uniform in all directions? The cosmic microwave background radiation, which is essentially the afterglow of the Big Bang, shows temperature variations of only 1 part in 100,000. This consistency posed a puzzle for scientists, because regions of space that are vastly distant from each other shouldn't have been able to equilibrate their temperatures given the age of the universe and the speed of light. The theory of cosmic inflation provides an elegant solution. Before inflation, these regions were close enough to interact and reach the same temperature. Then, the period of rapid expansion stretched them far apart, preserving this thermal equilibrium across vast distances. This explains why when we look at opposite sides of the observable universe, we see such similar conditions. As the universe continued to expand and cool after this initial inflation, the first fundamental particles began to form. These weren't yet the atoms we know today, but rather a soup of subatomic particles. The universe was still too hot for atoms to exist. It would take about 380,000 years before the universe cooled enough for the first atoms to form, a period scientists call recombination. This early universe was dramatically different from what we see today. There were no stars, no galaxies, not even the simplest elements beyond hydrogen and helium, with trace amounts of lithium. These primary elements were forged in what scientists call the Big Bang nucleosynthesis, the period when the universe was cool enough for atomic nuclei to form, but still too hot for complete atoms. The distribution of these primordial elements provides one of the strongest pieces of evidence for the Big Bang theory. When we look at the oldest stars and galaxies, we find exactly the ratio of elements that the Big Bang theory predicts. About 75% hydrogen and 25% helium, with just a tiny trace of lithium. As the universe expanded further, gravity began to play a crucial role. Slight variations in the density of matter, which originated from quantum fluctuations during the inflation period, began to grow. Areas with slightly more matter attracted additional matter through gravitational pull. These dense regions would eventually become the cosmic web of galaxies we see today. But the expansion of the universe didn't slow down as many scientists initially expected. In the late 1990s, observations of distant supernovas revealed something astonishing. The universe's expansion is actually accelerating. This discovery led to the hypothesis of dark energy, a mysterious force that appears to be pushing the universe apart at an ever-increasing rate. Today, we can see the results of this 13.8 billion-year journey all around us. When we look up at the night sky, we're seeing light that has traveled across vast expanses of space and time. The nearest stars we can see with our naked eye are sending us light that left them years ago. When we look at distant galaxies, we're seeing them as they appeared millions or even billions of years ago. This brings us to one of the most profound aspects of the Big Bang. It marked the beginning of time itself. There was no before the Big Bang, because time as we understand it began at that moment. It's a concept that challenges our everyday understanding of cause and effect, but it's supported by our best physical theories and observations. As we continue to study the birth of our universe, new questions arise. What caused the initial inflation? What existed before the Big Bang, if anything? What is the nature of dark energy that drives the universe's acceleration? These questions push the boundaries of our current scientific understanding and remind us that there is still much to learn about our cosmic origins. The story of the Big Bang connects directly to our previous discussion about stellar evolution. Without this cosmic beginning, without the precise conditions that allowed matter to form and gravity to shape the first stars, none of the elements that make up our bodies would exist. We are not just star stuff. We are the children of a universe that has been expanding and evolving for 13.8 billion years. From the cosmic birth of the Big Bang, our universe has evolved into a spectacular display of light and color. When you look up at the night sky, you might notice that stars aren't all the same color. Some appear blue, others white, and still others have a distinct reddish hue. These colors aren't random. They're nature's thermometer, telling us precisely how hot each star is. Let's start with the hottest stars we can see. These appear blue or blue-white to our eyes, and they're absolutely scorching, with surface temperatures reaching up to 40,000 Kelvin. That's more than 6 times hotter than our Sun. Stars like Spica, which you can find in our night sky, shine with this intense blue color, revealing their extreme temperatures of around 25,000 Kelvin. Moving down the temperature scale, we find white stars like Vega, which astronomers use as a standard reference point. These stars burn at around 10,000 Kelvin. They're still incredibly hot, but not as extreme as their blue counterparts. When astronomers measure star colors, they actually use Vega as a baseline, setting it as their 0 point for color measurements. Our own Sun, with a surface temperature of about 6,000 Kelvin, appears yellow-white. Interestingly, if we could see the Sun from space, it would look pure white, shining with nearly equal amounts of all visible colors. The reason it appears yellow from Earth is because our atmosphere scatters blue light more effectively than red light. This same scattering effect explains why our sky appears blue during the day. Even cooler are the orange stars like Aldebaran, with temperatures around 4,000 Kelvin. These stars are entering their senior years, having burned through much of their nuclear fuel. Their cooler temperatures result in light that shifted toward the redder end of the spectrum, giving them their distinctive orange glow. The coolest stars we can see shine in deep red colors. Stars like Betelgeuse have surface temperatures of only about 3,000 Kelvin. While this might seem blazing hot by earthly standards, remember that it's less than half the temperature of our Sun. These red stars are often giants, having swelled up as they near the end of their lives. But how do astronomers measure these colors with precision? They can't simply look at a star and guess its temperature. Instead, they use a sophisticated system of filters that measure light at specific wavelengths. The most common system uses 3 filters: ultraviolet, blue, and visual yellow. By measuring how bright a star appears through each filter, astronomers can calculate what they call a color index. This color index works because of a fundamental law of physics called Wien's law, which tells us that hotter objects emit more of their light at shorter wavelengths, while cooler objects emit more at longer wavelengths. This is why a piece of metal glows red when it's hot, but turns blue-white when it's even hotter. Stars follow the exact same principle. The relationship between color and temperature is so reliable that astronomers can determine a star's temperature just by measuring its color, even if that star is thousands of light years away. The bluest stars with a color index of -0.4 are the hottest at around 40,000 Kelvin. The reddest stars with a color index of +2.0 are the coolest at about 2,000 Kelvin. Our Sun, with its yellow-white appearance, has a color index of about +0.65. Looking at a star cluster through a telescope reveals this temperature range in beautiful detail. Stars of different colors sparkle like cosmic jewels against the black velvet of space. In regions like the Sagittarius star cloud, we can see thousands of stars displaying their temperatures through their colors, from the hot blue stars to the cool red ones. These colors tell us more than just temperature. They provide clues about a star's mass, age, and eventual fate. The hottest blue stars tend to be the most massive and burn through their fuel the fastest, living only a few million years. Cooler orange and red stars can shine for billions or even trillions of years. Our yellow Sun sits comfortably in the middle, with a lifespan of about 10 billion years. Understanding stellar colors helps us piece together the life cycles of stars. We can identify young, hot stars in stellar nurseries, middle-aged stars like our Sun in stable adulthood, and aging red giants nearing the end of their lives. This rainbow of stellar colors paints a picture of the continuous cycle of stellar birth, life, and death that we discussed earlier. When you next look up at the night sky, remember that each star's color is telling you its story. The brilliant blue stars are the bold but short-lived giants of the cosmos. The steady yellow stars, like our Sun, are the main sequence middleweights. And those red stars are the cooler, older members of our celestial community, each one contributing to the spectacular light show above our heads. This cosmic palette, from the hottest blues to the coolest reds, reminds us that we live in a dynamic universe where stars are not eternal and unchanging, but rather go through their own life cycles, marked by changes in temperature and color. It's another piece in our understanding of the vast cosmic story that began with the Big Bang and continues in the stellar furnaces that light up our night sky. Now that we understand how stars paint the cosmos with their varied temperatures and colors, let's find our place within this grand celestial canvas. Our home, the Milky Way, is a massive barred spiral galaxy that's been spinning through space for 13.6 billion years. If you could somehow view it from above, you'd see a majestic disk of stars, gas, and dust stretching 100,000 light-years across. Think of the Milky Way like a cosmic city. At its heart lies downtown, a peanut-shaped central bulge measuring 10,000 light-years across. This galactic downtown houses 10 billion stars, mostly ancient red giants that formed in the galaxy's early days. At the very center of this bulge lurks something extraordinary, a supermassive black hole called Sagittarius A star with a mass equal to 4 million suns. Our solar system doesn't reside in this bustling downtown district. Instead, we make our home in what you might call the cosmic suburbs, about 26,000 light-years from the galactic center. We're situated in one of the galaxy's spiral arms, specifically a smaller neighborhood called the Orion Cygnus Arm, sometimes known as the Local Arm or Orion Spur. This modest spiral arm is sandwiched between two larger arms, Perseus on one side and Carina Sagittarius on the other. Our cosmic neighborhood is constantly in motion. Our entire solar system orbits around the galactic center at the astonishing speed of 515,000 miles per hour. Yet, despite this breakneck pace, it takes us about 250 million years to complete a single orbit. The last time our solar system was in this exact position, dinosaurs were just beginning to roam the Earth, and mammals had not yet evolved. The Milky Way's structure is more complex than just a simple disk. The galactic disk itself is 1,000 light-years thick, sprinkled with about 200 billion stars. These stars aren't evenly distributed, but are gathered into spiral arms that wind outward from the central bulge. The Milky Way has 4 main spiral arms, 2 major ones called Perseus and Scutum Centaurus, and 2 minor ones including our own local arm. Surrounding this disk and bulge are globular clusters, ancient collections of stars that orbit the galaxy like satellites. Beyond these, an enormous spherical halo of dust and gas extends outward, twice as wide as the disk itself. But there's something even more mysterious. Astronomers believe our entire galaxy is embedded in an enormous halo of invisible dark matter, which makes up about 90% of our galaxy's mass. This cosmic architecture creates the breathtaking view we see on clear, dark nights. When we look up at the milky band of light stretching across the sky, we're actually seeing the edge-on view of our galaxy's disk, peering through layers of stars, gas, and dust toward the galactic center. The darker patches in this glowing band are vast clouds of cosmic dust, blocking the light from more distant stars. Our position in the galactic suburbs turns out to be quite fortunate. The galactic center, while spectacular to view, is a chaotic place where stars are packed much more closely together. The intense radiation and gravitational forces there might make it difficult for life as we know it to exist. Our location in the quieter outskirts provides us with a stable environment and a fantastic view of the cosmic city we call home. Interestingly, our solar system doesn't orbit perfectly in line with the galaxy's disk. We're tilted at an angle of about 63 degrees relative to the galactic plane. As one scientist described it, we're essentially sailing through the galaxy sideways. Currently, we're riding along a massive wave of interstellar gas that stretches 9,000 light-years long and undulates above and below the galactic disk. The total mass of our galactic home, including the invisible dark matter, equals about 1.5 trillion times the mass of our Sun. While we can see only about 200 billion stars, astronomers estimate there might be more than 100 billion planets in our galaxy. Most of these worlds remain undiscovered, as we've only found a few thousand so far. Our current understanding of the Milky Way has been dramatically improved by space telescopes, particularly the European Space Agency's Gaia mission. Before such precise measurements were possible, studying our galaxy's structure was like trying to map a forest while being lost in the middle of it. Now we can measure the positions and motions of more than 1 billion stars with unprecedented accuracy. As we conclude our tour of our cosmic address, remember that we're part of something truly magnificent. Every star you see in the night sky is our neighbor in this vast galactic city. The light from distant stars has traveled hundreds or thousands of years to reach your eyes, telling the story of our dynamic and ever-changing galactic home. When you next look up at that glowing band of the Milky Way, you'll know exactly where you are. In the galactic suburbs, spinning through space in an elegant cosmic dance that's been ongoing for billions of years. The story of a star begins in the vast clouds of gas and dust that float through space. These stellar nurseries, called nebulae, contain primarily hydrogen and helium left over from the Big Bang, along with heavier elements scattered by previous generations of stars. Under the relentless pull of gravity, portions of these clouds begin to collapse inward. As the material draws together, the pressure and temperature at the center of the collapsing cloud steadily increase. When the core temperature reaches about 15 million degrees, something remarkable happens. The intense heat and pressure strip electrons from their atoms, creating a plasma of charged particles. Under these extreme conditions, hydrogen nuclei begin to crash into each other with enough force to overcome their natural electrical repulsion. These nuclei fuse together, releasing enormous amounts of energy in the process. This is the moment of stellar birth, when nuclear fusion ignites and a star begins to shine. A star will spend most of its life in what astronomers call the main sequence phase, steadily converting hydrogen into helium through nuclear fusion. The energy released by fusion creates an outward pressure that perfectly balances the inward pull of gravity, keeping the star stable. Our Sun is currently in this phase and has been for about 4.6 billion years. The length of a star's life depends almost entirely on its initial mass. More massive stars burn through their fuel much more quickly than smaller ones. A star 10 times more massive than our Sun might live only a few million years, while a star with half the Sun's mass could shine for over 100 billion years. When a star begins to exhaust the hydrogen fuel in its core, dramatic changes occur. With less fusion taking place, the outward pressure decreases and gravity begins to compress the core. This compression actually heats the surrounding layers of hydrogen, causing them to fuse more rapidly. The star's outer layers expand dramatically in response to this new energy production, cooling as they expand. The star has now become a red giant. For stars like our Sun, the red giant phase marks the beginning of the end. The core continues to contract and heat up until it reaches temperatures high enough to fuse helium into carbon. This provides a brief reprieve, but eventually the helium fuel runs out too. In stars with masses similar to our Sun, the temperatures never get high enough to fuse carbon into heavier elements. Instead, these medium-mass stars begin to pulsate, shedding their outer layers into space. These ejected layers form a beautiful ring of gas called a planetary nebula. The core of the star, now exposed, becomes a white dwarf. About the size of Earth, but containing roughly half the mass of the original star, white dwarfs are incredibly dense. With no fuel left to burn, they will spend billions of years gradually cooling and dimming until they become cold, dark objects called black dwarfs. But the story takes a dramatically different turn for stars more than about 5 times the mass of our Sun. When these massive stars reach the red giant phase, they become red supergiants, growing far larger than their less massive counterparts. Their cores can reach temperatures high enough to fuse carbon and then oxygen, neon, magnesium, and silicon, creating progressively heavier elements. This process continues until iron begins forming in the core. Iron marks a crucial turning point because fusing iron nuclei requires more energy than it releases. When the core becomes mostly iron, fusion ceases. Without the outward pressure from nuclear fusion to counteract gravity, the core collapses catastrophically in less than a second. The temperature soars to over 100 billion degrees as the iron atoms are crushed together. The core becomes so compressed that electrons are forced to combine with protons, forming neutrons. A shockwave rebounds from this compressed core, racing outward through the star's layers. This triggers a tremendous explosion called a supernova, which can briefly outshine an entire galaxy. During a supernova, the extreme temperatures and pressures create conditions where elements heavier than iron can form. The explosion scatters these newly forged elements across space, enriching the gas between stars with the building blocks for future stars and planets. This is how elements like gold, silver, and uranium came to exist in our universe. What remains after a supernova depends on the initial mass of the star. For stars between about 5 and 15 times the mass of our Sun, the core remains intact as a neutron star, an object so dense that a teaspoonful of its material would weigh billions of tons on Earth. These strange objects spin rapidly, sometimes making complete rotations in just seconds, and possess magnetic fields trillions of times stronger than Earth's. For stars more than 15 times the mass of our Sun, even the neutrons cannot withstand the crush of gravity. The core continues to collapse until it becomes a black hole, an object so dense that not even light can escape its gravitational pull. The boundary around a black hole, called the event horizon, marks the point of no return. Anything that crosses this boundary can never escape. This cycle of stellar birth, life, and death continues throughout the universe. The nebulae where new stars form are enriched by the elements created and scattered by dying stars, making each new generation of stars slightly different from the one before. Through this process, the cosmos gradually fills with the elements necessary for planets, complex chemistry, and even life itself. Our cosmic neighborhood, known as the solar system, is an intricate family of celestial bodies, all bound together by the Sun's gravitational influence. At the center of it all sits our star, containing 99.86% of all the system's mass. Its powerful gravity orchestrating a complex celestial dance that's been ongoing for 4.6 billion years. The most prominent members of our solar family are the 8 planets, each with its own unique character. These worlds can be divided into 2 distinct groups: the inner terrestrial planets and the outer giant planets, with an asteroid belt serving as a natural boundary between them. Let's start our tour with the 4 terrestrial planets, rocky worlds closest to the Sun. Mercury, the smallest planet, orbits between 0.31 and 0.59 astronomical units from the Sun. Its surface is marked by vast cliffs and impact craters, experiencing extreme temperature swings from -170 degrees Celsius at night to 420 degrees Celsius during the day. Venus, Earth's closest planetary neighbor, orbits between 0.72 and 0.73 astronomical units from the Sun. Often called Earth's twin due to its similar size, Venus has a thick carbon dioxide atmosphere that creates an extreme greenhouse effect, making it the hottest planet in our solar system, despite not being the closest to the Sun. Our own planet Earth orbits between 0.98 and 1.02 astronomical units from the Sun, in the perfect position for liquid water to exist on its surface. It's the only world we know that harbors life, with its nitrogen and oxygen atmosphere, global oceans, and complex weather systems, making it uniquely habitable. Mars, the red planet, orbits between 1.38 and 1.67 astronomical units from the Sun. Though only half the size of Earth, it features the solar system's largest volcano and deepest canyon. Its rusty red color comes from iron oxide in its soil, and its polar regions are capped with frozen water and carbon dioxide ice. Beyond Mars lies the asteroid belt, a region between 2.3 and 3.3 astronomical units from the Sun. This band contains tens of thousands of rocky bodies, including the dwarf planet Ceres. Despite its crowded nature, the total mass of the asteroid belt is less than 1,000th that of Earth. Moving outward, we encounter the giant planets, beginning with Jupiter, the largest world in our solar system. Jupiter alone contains more mass than all other planets combined, with its great red spot storm being larger than Earth itself. The gas giant maintains a family of 95 moons, including the 4 large Galilean satellites, Ganymede, Callisto, Io, and Europa. Saturn, famous for its spectacular ring system, comes next. Its rings are composed of countless pieces of ice and rock, some as tiny as dust grains, others as large as buildings. Saturn hosts 146 known moons, with Titan being the only moon in the solar system to have a substantial atmosphere. The ice giants Uranus and Neptune complete our planetary family. Uranus is unique for rotating on its side, likely due to a massive collision in its past. It appears as a blank blue-green orb due to methane in its atmosphere and is orbited by 28 known moons. Neptune, the windiest planet, has sustained winds reaching 2,000 kilometers per hour and is orbited by 16 known moons, including the unusual retrograde rotating Triton. Beyond Neptune's orbit lies the Kuiper belt, a region similar to the asteroid belt, but much larger and composed primarily of icy bodies. The region is home to several dwarf planets, including Pluto, Haumea, and Makemake. These distant worlds, along with others like Eris in the scattered disk, represent a new class of solar system objects that help us understand the system's outer reaches. The solar system also hosts numerous comets, which spend most of their time in the distant Oort cloud, but occasionally venture into the inner solar system. When they do, the sun's heat causes their ices to sublimate, creating the characteristic tails that have fascinated humanity for millennia. All these bodies move through a sea of interplanetary material, from microscopic dust particles to small meteoroids. This material, along with the solar wind from the sun, fills the vast spaces between planets, creating an interconnected environment that extends out to the heliopause, where our sun's influence gives way to interstellar space. The architecture of our solar system tells a story of its formation. The terrestrial planets formed close to the sun, where only metals and rocky materials could survive the intense heat. The giant planets formed beyond what astronomers call the frost line, where water and other volatiles could remain frozen, allowing them to grow much larger than their rocky inner siblings. Each member of our solar family plays a crucial role in the system's stability. Jupiter's massive gravitational influence helps protect the inner planets from too many cometary impacts, while the complex gravitational dance between planets and their moons helps maintain orbits and creates phenomena like Saturn's rings and Jupiter's radiation belts. Our knowledge of this cosmic family continues to grow as we send robotic explorers to visit these worlds. Each new mission reveals more details about our celestial neighbors, from the active geology of Pluto to the potential subsurface oceans on several icy moons. These discoveries remind us that although we've mapped the major players in our solar system, there are still many mysteries waiting to be solved in our cosmic backyard. In our journey through the cosmos, we now encounter one of the most fascinating aspects of astronomy: the finite speed of light. Moving at precisely 299,792 kilometers per second, light seems incredibly fast by everyday standards, but the vast distances of space reveal just how long it takes light to travel across the universe. This cosmic speed limit was first discovered by Ole Romer in 1676, when he observed that the moons of Jupiter appeared to move more slowly when Earth was moving away from Jupiter than when it was approaching. This led him to conclude that light must travel at a finite speed, taking about 22 minutes to cross the diameter of Earth's orbit. To understand just how this cosmic speed limit affects our view of the universe, let's start close to home. Light from our moon takes about 1.3 seconds to reach Earth. This means when you look at the moon, you're seeing it as it was a little more than a second ago. While this delay might seem insignificant, it becomes more dramatic as we look further out into space. Sunlight takes approximately 8 minutes and 17 seconds to travel from the sun's surface to Earth. This means if the sun were to suddenly disappear, we wouldn't know about it for over 8 minutes. We would continue to see its light and feel its warmth, even though it was already gone. This delay between an event happening and our ability to observe it grows larger with distance. When we look at the nearest star system to Earth, Alpha Centauri, we're seeing it as it appeared about 4.2 years ago. The light we observe today began its journey when that star system looked quite different from how it appears right now. This concept of looking back in time becomes even more pronounced when we observe more distant objects. The implications of light's finite speed create what astronomers call the light travel time effect. When we look deep into space, we're essentially looking back in time. The further away an object is, the further back in time we see it. This creates a unique challenge for astronomers. We can never know what distant objects look like right now. We can only see them as they were when their light began its journey to Earth. Consider the Andromeda Galaxy, our nearest large galactic neighbor. The light we see from Andromeda today left that galaxy 2.5 million years ago, when our early human ancestors were just beginning to walk upright. We're not seeing Andromeda as it exists now, but rather as it existed during the early Stone Age on Earth. This delay in light travel time becomes even more significant when we look at more distant galaxies. The light from some of the most distant galaxies observable by our telescopes has been traveling for over 13 billion years, more than 90% of the age of the universe. When we observe these ancient galaxies, we're seeing them as they appeared shortly after the Big Bang, providing us with a window into the early universe. The finite speed of light also has practical implications for space exploration and communication. When NASA communicates with Mars rovers or other spacecraft, radio signals, which travel at the speed of light, can take anywhere from 4 to 24 minutes to make a one-way trip, depending on the constantly changing distance between Earth and Mars as both planets orbit the Sun. This communication delay means that remote control of spacecraft must account for the time it takes commands to reach them and for confirmation signals to return. This cosmic speed limit ensures that no information or influence can travel faster than light. This fundamental constraint of the universe, established by Einstein's theory of special relativity, means that we can never have truly instantaneous communication or observation of distant space events. Everything we observe in the cosmos comes with an inherent delay proportional to its distance from us. The speed of light also provides astronomers with a convenient way to measure cosmic distances. Rather than using conventional units like kilometers, astronomers often use the light year, the distance light travels in 1 year, which is approximately 9.46 trillion kilometers. This unit helps convey both the vast distances involved in astronomy and the time it takes light to travel these distances. For even larger distances, astronomers use the parsec, equal to about 3.26 light years. The nearest star to our solar system, Proxima Centauri, is about 1.3 parsecs away, meaning its light takes 4.2 years to reach us. The center of our Milky Way galaxy is approximately 26,000 light-years distant, so when we observe it, we're seeing it as it appeared when Earth was in the midst of the last ice age. Understanding that light takes time to travel has revolutionized our view of the universe. When we look up at the night sky, we're not seeing a cosmic snapshot of the present moment, but rather a complex tapestry of different times, all visible to us at once. Nearby stars appear as they were a few years ago, while distant galaxies are seen as they were millions or billions of years in the past, creating a unique view of cosmic history written in light across the night sky. Now that we understand how light travels across the vast distances of space, let's explore where most of this light comes from. Stars are nature's most powerful energy generators, cosmic furnaces that have been lighting up the universe for billions of years through an extraordinary process called nuclear fusion. The story of a star's furnace begins in the dense clouds of gas and dust scattered throughout space. When gravity pulls enough of this material together, a protostar forms from the collapsing cloud. If this developing star accumulates enough mass, about 0.08 times the mass of our Sun, something remarkable happens. The immense gravitational pressure at its core creates temperatures hot enough to trigger nuclear fusion. This fusion process is what truly defines a star. Deep within their cores, stars are so hot and dense that hydrogen atoms are stripped of their electrons, creating a plasma of charged particles. Under temperatures of millions of degrees and crushing pressures, hydrogen nuclei overcome their natural electrical repulsion and fuse together to form helium. This nuclear fusion releases an enormous amount of energy in the process. The balancing act between gravity pulling inward and fusion pressure pushing outward is what keeps a star stable during its main sequence life. About 90% of all stars in the universe, including our Sun, are main sequence stars actively fusing hydrogen into helium in their cores. This stability can last for millions to billions of years, depending on the star's mass. Our Sun, which is a fairly average star, converts about 600 million tons of hydrogen into helium every second. Despite this enormous rate of fuel consumption, it has enough hydrogen to continue fusion for about 10 billion years total, with about 5 billion years still remaining in its main sequence life. The mass of a star determines everything about its life. More massive stars have stronger gravity, which creates higher core temperatures and faster fusion rates. While this means they shine more brightly, it also means they burn through their fuel much more quickly. A star 10 times more massive than our Sun will shine more than 1,000 times brighter, but it will exhaust its hydrogen fuel in only about 20 million years. On the other hand, smaller stars are more economical with their fuel. Red dwarf stars, which have about half the mass of our Sun, burn their hydrogen so slowly and efficiently that they can shine for 80 to 100 billion years. This is far longer than the current age of the universe, which is why every red dwarf star that has ever formed is still burning today. The temperature at a star's core also affects its color and brightness. More massive stars are hotter and appear blue, while less massive stars are cooler and appear red. Our Sun falls in between, giving it its characteristic yellow appearance. Blue stars can have surface temperatures of over 30,000 Kelvin, while red stars might be as cool as 3,000 Kelvin. Inside all these stellar furnaces, the outward pressure created by nuclear fusion perfectly balances with the inward pull of gravity, creating a state of equilibrium that astronomers call hydrostatic balance. This balance is crucial for the star's survival. If fusion pressure were to exceed gravitational pressure, the star would blow itself apart. If gravity were to win, the star would collapse. Not all concentrations of gas and dust become stars. Objects with less than 8% of our Sun's mass cannot achieve the core temperatures necessary for hydrogen fusion. These failed stars become brown dwarfs, objects more massive than planets, but not massive enough to sustain nuclear fusion in their cores. The relationship between a star's mass and luminosity was discovered in the early 20th century, leading to the creation of the Hertzsprung-Russell diagram. This important astronomical tool shows that main sequence stars form a distinct line when plotted by their temperature and brightness, with hot, bright, massive stars at one end and cool, dim, low-mass stars at the other. Eventually, all stars exhaust the hydrogen fuel in their cores. What happens next depends on the star's mass. Stars like our Sun will expand into red giants when they begin fusing helium into carbon. More massive stars can continue fusing heavier elements in their cores, while the most massive stars end their lives in spectacular supernova explosions. These stellar furnaces are responsible for creating most of the elements in the universe. While the lightest elements, hydrogen and helium, were formed in the Big Bang, nearly all other elements are forged through stellar nucleosynthesis, or in the violent deaths of massive stars. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all created inside stars that died long before our solar system formed. Understanding how stars generate their energy has been one of astronomy's greatest achievements. It explains not only why stars shine, but also how they evolve, why they have different colors, and ultimately how they create the elements necessary for life. These cosmic furnaces truly are the engines of the universe, transforming the simplest element, hydrogen, into all the building blocks needed for planets, atmospheres, and living things. While stars burn as cosmic furnaces throughout the universe, an even grander process is taking place on the largest scale imaginable. The entire cosmos is expanding, causing galaxies to drift apart from one another in a cosmic dance that has been ongoing since the Big Bang. This expansion shapes the very structure of our universe. This remarkable discovery was made by astronomer Edwin Hubble in 1929. By carefully measuring both the distances to other galaxies and the speed at which they were moving relative to Earth, Hubble found something astonishing. Not only were most galaxies moving away from us, but the farther away they were, the faster they appeared to be receding. To understand how astronomers measure these motions, we need to look at something called redshift. Just as a passing vehicle's sound changes pitch as it moves past us, light from moving objects experiences a similar effect. When a galaxy moves away from us, the wavelengths of its light are stretched, shifting them toward the red end of the spectrum. The faster the galaxy moves away, the greater this redshift becomes. Hubble's observations led to what we now call Hubble's law, which states that a galaxy's apparent recession speed is proportional to its distance from us. This relationship is so fundamental to our understanding of the cosmos that astronomers now use it as a tool. By measuring a galaxy's redshift, they can calculate its distance from Earth. But this universal expansion isn't like an explosion where galaxies are simply flying apart through space. Instead, space itself is expanding, carrying the galaxies along with it. Astronomers often use the analogy of a rising fruitcake in an oven. As the cake bakes and expands, all the raisins move further apart from each other, not because they're moving through the cake, but because the cake itself is expanding. This expansion affects every region of space, but its effects become more dramatic over larger distances. While nearby galaxies might drift apart relatively slowly, galaxies billions of light years away appear to be racing away from us at tremendous speeds. This is simply because there is more expanding space between us and more distant galaxies. However, the universe's expansion doesn't affect everything equally. The force of gravity can overcome this expansion on smaller scales. Individual galaxies stay together rather than being torn apart. Even clusters of galaxies can remain gravitationally bound to each other. Our own Milky Way belongs to a collection of about 85 galaxies called the local group. In fact, some nearby galaxies can even move toward each other under the influence of gravity. The Andromeda Galaxy, our nearest large galactic neighbor, is actually moving toward the Milky Way. Unlike the redshift seen in most galaxies, Andromeda shows a blue shift, indicating it is approaching rather than receding. In a few billion years, the Milky Way and Andromeda will collide and merge into a single larger galaxy. The discovery that the universe is expanding was revolutionary when it was first made. Before this, many scientists believed the universe was static and unchanging. Some, including Albert Einstein, had even modified their theories to try to force the universe to be static. The observational evidence of expansion helped establish our modern understanding of a dynamic, evolving cosmos. This expansion also tells us something profound about the history of the universe. If we imagine running time backward, an expanding universe implies that everything was closer together in the past. Following this logic back far enough leads to the conclusion that the universe began in an extremely hot, dense state, what we now call the Big Bang. Today, astronomers continue to refine our understanding of cosmic expansion. They've discovered that the expansion isn't steady, but is actually accelerating. Galaxies are moving apart faster and faster as time goes on. This acceleration is one of the biggest mysteries in modern cosmology, attributed to something called dark energy, which seems to permeate all of space. The expanding universe also creates some counterintuitive effects. Because light takes time to travel across space, and space is expanding as the light travels, the observable universe is much larger than one might expect. Light from the most distant galaxies we can see has been traveling for over 13 billion years, during which time the expansion of space has carried these galaxies even further away. Understanding the universe's expansion helps us comprehend our cosmic context. We live in a dynamic universe that continues to evolve and change. Every galaxy we see is part of this grand cosmic dance, moving through expanding space in a pattern that extends across billions of light years. This expansion may eventually determine the ultimate fate of our universe, whether it will expand forever or perhaps someday reverse course. As we gaze out at the night sky, we're not just seeing billions of stellar furnaces scattered through space. We're witnessing evidence of a cosmos in constant motion, where space itself stretches ever outward, carrying galaxies along in a cosmic ballet that began with the Big Bang and continues to this day. As galaxies dance through the expanding cosmos, our own planet Earth occupies a remarkable position in space that makes it uniquely suited for life. Often called the Goldilocks planet, Earth sits in a special region around the Sun where conditions are just right, neither too hot nor too cold, allowing for the existence of liquid water on its surface. This perfect positioning is what scientists call the habitable zone, a narrow band around any star where temperatures allow water to exist as a liquid. If Earth orbited slightly closer to the Sun, like Venus, our oceans would boil away into space. If we orbited slightly further out, like Mars, that same water would be permanently frozen. Instead, Earth maintains the perfect distance where water can flow freely across its surface. But location alone isn't enough to make a planet habitable. Earth possesses several crucial features working in harmony to create and maintain conditions suitable for life. One of the most important is our atmosphere, a complex mixture of gases that serves multiple vital functions. This gaseous envelope acts as an insulating blanket, helping to regulate temperature and prevent the extreme swings that would make life impossible. Our atmosphere also serves as the first line of defense against cosmic threats. It absorbs and filters much of the harmful ultraviolet radiation from the sun, preventing it from reaching the surface and damaging living organisms. Without this protective layer, life as we know it could not exist on Earth's surface. Complementing our atmosphere is Earth's remarkable magnetic field, generated by our planet's molten iron core. This invisible shield extends far into space, creating a protective bubble called the magnetosphere that deflects dangerous charged particles from solar winds and cosmic rays. This magnetic shield works in partnership with the atmosphere, preventing these powerful solar winds from gradually stripping away our protective atmospheric layer, as happened on Mars billions of years ago. The relationship between Earth's atmosphere and magnetic field creates a formidable defense system. While the magnetic field preserves the atmosphere by deflecting solar winds, the atmosphere provides additional protection against radiation that penetrates the magnetic shield. This partnership has been crucial in maintaining Earth's habitability over billions of years. Earth's dynamic nature also plays a vital role in its habitability. Our planet's system of plate tectonics helps regulate the climate by controlling the carbon dioxide cycle. This process, combined with the water and carbon cycles, constantly recycles and replenishes the planet's natural resources, sustaining life over geological timescales. Water itself is perhaps the most crucial ingredient for life on Earth. Its presence in liquid form allows it to act as a universal solvent, dissolving and transporting various molecules necessary for life. Water's unique properties also help regulate our planet's temperature. Its ability to absorb large amounts of heat helps moderate climate, while its unusual property of being less dense as a solid allows ice to float, preventing bodies of water from freezing solid and protecting aquatic life during cold periods. Comparing Earth to its nearest neighbors helps illustrate just how special our planet's conditions are. Venus, similar to Earth in size, suffers from a runaway greenhouse effect that creates surface temperatures hot enough to melt lead. Mars, while showing evidence of past water, lacks both a strong magnetic field and substantial atmosphere, resulting in extreme temperature swings and exposure to harmful radiation. The delicate balance that makes Earth habitable becomes even more apparent when we study newly discovered planets around other stars. While some of these exoplanets exist in their stars' habitable zones, potentially harboring liquid water, they must also possess the right combination of atmospheric composition, magnetic fields, and geological activity to truly support life as we know it. This understanding of what makes Earth special has profound implications for our search for life elsewhere in the universe. As we explore distant solar systems, we look not only for planets in the habitable zone, but also for evidence of atmospheres, magnetic fields, and other features that mirror Earth's life-supporting characteristics. Our planet's position and properties represent a remarkable confluence of factors that create a cosmic oasis. From its perfect orbital distance to its protective shields, from its dynamic geological processes to its life-sustaining water cycle, Earth demonstrates the extraordinary conditions required for a planet to nurture and sustain life. As we continue to explore the cosmos and search for other habitable worlds, we gain an ever deeper appreciation for the rare and precious nature of our planetary home. Gravity is the invisible force that orchestrates every movement in the cosmos, from the way planets orbit stars to the grand structure of galaxies themselves. Think of it as cosmic glue, an attractive force between any objects that have mass. The more massive an object is, the stronger its gravitational pull becomes. In our solar system, the Sun's enormous mass creates a powerful gravitational field that extends far into space. This gravitational pull acts like an invisible lasso, keeping all the planets tethered in their orbits. Each planet responds to this pull while also moving forward through space, creating a perfect balance that results in orbital motion. When a planet orbits the Sun, two forces work together to maintain its path. The Sun's gravity constantly pulls the planet inward, while the planet's own motion creates an outward pushing force. This delicate balance prevents planets from either crashing into the Sun or flying off into space. It is like a cosmic game of tug-of-war that never ends. The closer a planet is to the Sun, the stronger the gravitational pull it experiences. This explains why inner planets like Mercury orbit much faster than outer planets like Neptune. Mercury completes an orbit in just 88 Earth days, while Neptune takes 165 Earth years to make a single trip around the Sun. Planetary orbits are not perfect circles, but slightly oval-shaped paths called ellipses. The shape of an orbit depends on its eccentricity, which measures how much it deviates from a perfect circle. Venus has a nearly circular orbit with very low eccentricity, while Mercury has a more elongated eccentric orbit. These variations in orbit shapes are all governed by the interaction between gravity and motion. Beyond our solar system, gravity shapes the structure of entire galaxies. The combined gravitational pull of billions of stars helps hold galaxies together, preventing them from flying apart as they rotate. This same force causes galaxies to form into distinctive spiral or elliptical shapes and even determines how they interact when they pass near each other. Gravity also creates natural groupings of celestial objects. Just as the Sun's gravity keeps its family of planets together, galaxies often form clusters held together by their mutual gravitational attraction. Our own Milky Way is part of a cluster called the Local Group, which contains about 85 galaxies bound together by gravity. On an even larger scale, gravity is responsible for the cosmic web, the largest known structure in the universe. This web consists of vast filaments of galaxies and dark matter, all drawn together by gravitational attraction across billions of light years. The spaces between these filaments form enormous cosmic voids, creating a structure that resembles a gigantic spider web spanning the observable universe. Closer to home, gravity affects the shape of large celestial bodies. When an object becomes massive enough, its own gravity pulls it into a spherical shape. This is why large planets and stars are nearly perfect spheres, while smaller objects like asteroids can have irregular shapes. The point at which an object becomes massive enough for gravity to make it spherical is called the hydrostatic equilibrium. Gravity plays a crucial role in the life cycles of stars. When a cloud of gas and dust becomes massive enough, gravity causes it to collapse inward, eventually triggering nuclear fusion and creating a new star. Later in a star's life, gravity continues to compress its core as it runs out of fuel, leading to various end states like white dwarfs, neutron stars, or black holes, depending on the star's initial mass. Black holes represent gravity at its most extreme. In these objects, gravity is so strong that not even light can escape once it passes the event horizon. The gravitational field of a black hole can even bend the path of light that passes nearby, creating phenomena like gravitational lensing that astronomers use to study the universe. Gravity also orchestrates dramatic cosmic events. When galaxies pass too close to each other, their mutual gravitational attraction can pull them into a cosmic dance that eventually ends in a collision and merger. Our own Milky Way is destined to collide with the Andromeda Galaxy in about 4 billion years, a process governed entirely by the gravitational attraction between these two massive star systems. Imagine living next to a massive nuclear reactor that's been running for 4.5 billion years. That's exactly what we're doing right now. Our Sun, this seemingly eternal beacon in our sky, is actually quite the character among stars, and recent discoveries have shown it's more unique than we ever imagined. Picture the Sun as the laid-back neighbor in a street full of hyperactive stars. While other middle-aged stars like itself are throwing massive stellar tantrums, our Sun takes a more relaxed approach to life. Scientists studying 369 stars similar to our Sun discovered something remarkable. These stellar twins are up to 5 times more active than our own star, even during its most energetic periods. But don't let this relaxed attitude fool you. Our Sun still puts on quite a show. Every 11 years, it goes through a complete personality change, a cycle that astronomers have been watching since the 1600s, when Galileo first pointed his telescope at its glowing surface. During these cycles, the Sun's activity rises and falls like the rhythm of a cosmic heartbeat. At the peak of these cycles, hundreds of sunspots can appear on the Sun's surface. These aren't just simple dark spots, they're intense magnetic storms, each one large enough to swallow Earth several times over. Alongside these spots come solar flares, massive eruptions that can unleash more energy in a few minutes than humans could generate in 1,000,000 years. These solar phenomena aren't just cosmic fireworks. When they're directed at Earth, they create spectacular auroras, those dancing lights in our polar skies. But they can also disrupt our technology, interfering with satellite communications, power grids, and navigation systems. It's like our laid-back neighbor occasionally throws a party so wild it affects the entire neighborhood. What makes our Sun truly fascinating is its current phase of life. Like humans, stars go through different life stages, and our Sun is solidly in its middle age. It's spent about 4.5 billion years steadily converting hydrogen into helium in its core, and it's got about another 5 billion years before major changes start happening. But unlike some middle-aged stars that are going through a midlife crisis with extreme activity, our Sun seems to be taking the peaceful route. Scientists have observed that our Sun is currently in what might be its quietest period in 9,000 years. This might sound like a long time, but in stellar terms, it's barely a coffee break. As one astronomer pointed out, 9,000 years in the life of our 4.5 billion-year-old Sun is equivalent to less than 45 minutes in the life of a 40-year-old person. The Sun's magnetic fields are the real conductors of this stellar symphony. As the star rotates, these fields get twisted and tangled, like rubber bands being wound up. When they snap and reconnect, they release enormous amounts of energy in the form of solar flares and coronal mass ejections. These magnetic fields also create the sunspots, areas where intense magnetic activity actually cools the surface slightly, making them appear darker against the bright background. But here's where our Sun shows its unique character. Those 369 similar stars studied by astronomers should be behaving just like our Sun. They have the same mass, the same temperature, the same age and the same chemical composition. Yet they're far more active. It's as if our sun is the cosmic equivalent of the dude from The Big Lebowski, taking it easy while its peers are working overtime. This relaxed behavior might be temporary, or it might be a sign of our sun entering a new phase of life. Some scientists think the sun might be going through a transition period, its magnetic field slowly changing as it ages. Others suggest we might just be living during an unusually quiet period, and our star could become more active in the future. The sun has just completed its weakest cycle in 200 years, and the next one, expected to peak around 2025, might be even weaker. But this doesn't mean our star is becoming less interesting. Even at its quietest, it's still pumping out enough energy every second to power human civilization for hundreds of thousands of years. Understanding our sun's behavior isn't just academic curiosity. Its activity directly affects our technology-dependent world. A major solar storm today could disrupt our power grids, disable satellites, and force airlines to reroute flights. The more we learn about our star's patterns and peculiarities, the better we can prepare for its occasional outbursts. The quest to understand our sun continues with each new generation of solar telescopes and observatories. Every observation reveals new mysteries about this relatively calm star that's chosen Earth's neighborhood as its home. While other similar stars are blazing through their middle age with dramatic displays of stellar activity, our sun maintains its steady, life-sustaining glow, proving that sometimes being a bit laid back isn't such a bad thing after all. Picture yourself standing at ground zero of the most devastating collision in Earth's history. 65 million years ago, a visitor from space the size of Mount Everest came hurling toward our planet at 40,000 miles per hour. This wasn't just any cosmic fender bender. This impact changed the entire course of life on Earth. When this massive asteroid struck what is now the Yucatan Peninsula, it unleashed the equivalent of 10,000 billion atomic bombs. The impact sent superheated rocks spraying across the globe, ignited worldwide forest fires, and kicked up so much dust that the sun was dimmed for months. In the aftermath, 85% of all species on Earth, including most dinosaurs, vanished forever. But here's the fascinating twist. If this catastrophic collision had never happened, mammals might never have risen to dominance. We humans might never have evolved. This single cosmic event redirected the entire story of life on our planet. It's a stark reminder that sometimes destruction paves the way for new beginnings. Yet this wasn't even the most dramatic collision in Earth's history. Travel back 4.5 billion years when our planet was still young. A wandering body the size of Mars slammed into Earth with such force that it liquefied both worlds. Debris from this cosmic crash was thrown into orbit around our battered planet. Over time, gravity pulled this molten material together, and within a month, our moon was born. The evidence for this incredible event is written in the rocks themselves. When astronauts brought back samples from the Apollo missions, scientists discovered something remarkable. Moon rocks share the exact same oxygen isotope signatures as Earth rocks, telling us they formed from the same original material. The Moon also has a surprisingly small iron core compared to Earth, exactly what we would expect if it formed from the outer layers of our planet that were torn away in the collision. These massive impacts weren't rare occurrences in the early solar system. They were the rule. Every planet bears the scars of countless collisions. Mercury's surface is pockmarked with craters. Mars sports the largest known impact basin in the solar system, a scar nearly half the size of the planet itself. Even today, Jupiter's powerful gravity regularly attracts comets and asteroids, earning it the nickname cosmic vacuum cleaner, helping protect the inner solar system from even more impacts. The cosmic demolition derby continues to this day. In 1994, astronomers watched in awe as comet shoemaker Levy 9 broke apart and slammed into Jupiter, leaving Earth-sized bruises in the giant planet's atmosphere. More recently, countless smaller objects continue to pummel planets and moons across our solar system. Even now, Earth receives roughly 100 tons of space material every single day. Most of these cosmic visitors are no larger than a grain of sand, creating brief, brilliant streaks across our night sky as they burn up in the atmosphere. But larger objects do get through. The Tunguska event of 1908 flattened 800 square miles of Siberian forest, and in 2013, a meteor exploded over Chelyabinsk, Russia, creating a shock wave that injured more than 1,000 people. But there's good news. Unlike the dinosaurs, we have the technology to spot potential impactors long before they reach Earth. Astronomers have already mapped about 90% of the largest near-Earth asteroids, those big enough to cause global catastrophes. We're also developing strategies to protect our planet. These range from using a spacecraft's tiny gravitational pull to nudge an asteroid off course, to more dramatic solutions like using nuclear devices to deflect incoming threats. Our planet itself has natural defenses against cosmic impacts. Earth's thick atmosphere acts like a shield, burning up countless small meteoroids before they can reach the ground. Any object smaller than 100 feet across is likely to break apart and explode before impact. Our atmosphere has protected us from devastating impacts for billions of years. The scars of ancient impacts are still visible on Earth today, though most have been erased by weather and geological processes. The mile-wide meteor crater in Arizona offers a pristine example of what happens when a cosmic projectile meets our planet. But even more impressive are the hidden craters, like the 100-mile-wide Chicxulub crater buried beneath Mexico's Yucatan Peninsula, site of that dinosaur-dooming impact. Through studying these cosmic collisions, we've learned that impacts do more than just create craters. They can change a planet's chemistry, alter its orbit, or even strip away its atmosphere. The planet Mercury, for instance, may have lost much of its original surface material in a massive ancient impact, explaining why this tiny world has such a large iron core relative to its size. These cosmic collisions don't just destroy, they also create. The same impacts that can cause mass extinctions also delivered water and organic compounds to the early Earth, perhaps providing some of the raw materials necessary for life itself. Every atom of gold in your jewelry was likely forged in the collision between neutron stars billions of years ago, before being scattered across space and eventually finding its way to Earth. In the vast cosmic theater of our universe, the most important actor never shows its face. Imagine a force so mysterious, so prevalent, that it makes up more than 80% of all matter in existence, yet remains completely invisible to our eyes and instruments. This is dark matter, perhaps the greatest cosmic puzzle of our time. The story of dark matter begins in the 1920s. when astronomers made a startling discovery. The stars in galaxies were moving far too fast. According to the laws of gravity that we know so well, these stellar objects should have been flung out into space, like a carousel spinning so quickly that its horses break free. Yet there they were, continuing their orderly dance around their galactic centers. Something invisible was holding these cosmic carousels together. The only explanation was that there must be more matter out there than we could see, matter that exerts a gravitational pull but emits no light, no radiation, no energy of any kind that we can detect. Astronomers called this invisible substance dark matter. Picture our own Milky Way galaxy. When we look up at the night sky, we see billions of stars, vast clouds of gas and dust, all the visible matter that makes up our cosmic neighborhood. But all of this, everything we can see with our most powerful telescopes, accounts for less than 20% of the galaxy's total mass. The rest is dark matter, spread out in a vast invisible halo that extends far beyond the visible edges of our galaxy. We see dark matter's influence everywhere we look in the cosmos. When astronomers study galaxy clusters, those enormous collections of hundreds or thousands of galaxies, they find the same pattern. The visible matter we can detect isn't nearly enough to generate the gravitational force needed to hold these massive cosmic structures together. Dark matter provides the extra gravitational glue. Even light itself reveals the presence of dark matter. Einstein showed us that massive objects can bend and distort light as it travels through space. By studying how light from distant galaxies is warped and distorted as it travels toward Earth, astronomers have created detailed maps of dark matter's distribution throughout the universe. These maps show dark matter forming an intricate cosmic web, with galaxy clusters forming at the points where these dark matter filaments intersect. But what exactly is dark matter? Scientists believe it's made of particles that barely interact with regular matter at all. These particles, called WIMPs, weakly interacting massive particles, pass right through normal matter like ghosts through walls. Every second, trillions of these particles may be passing through your body, yet you would never know it. Deep underground, in laboratories shielded from cosmic rays and other interference, scientists have built enormous detectors filled with tons of liquid xenon, hoping to catch the rare moment when a dark matter particle bumps into a normal atom. So far, these particles have proved frustratingly elusive. Other scientists search for dark matter using powerful particle accelerators, trying to create these mysterious particles in high-energy collisions. Some astronomers study mysterious signals from the center of our galaxy, where dark matter might be collecting in high concentrations. When dark matter particles collide, they could annihilate each other in tiny bursts of energy. The Fermi Space Telescope has detected an excess of gamma rays from the galactic center that might be the signature of these dark matter annihilations. The mystery of dark matter forces us to confront a humbling truth. After centuries of scientific progress, we find ourselves in a universe where most of the matter is completely invisible to us. We can only detect its presence through its gravitational effects on the visible matter we can see. It's as if we're watching a cosmic puppet show, able to see the puppets dance, but completely blind to the strings that control their movements. Different galaxies appear to contain different amounts of dark matter. Some galaxies seem to be made almost entirely of dark matter, while others appear to contain very little. This variation provides important clues about how galaxies form and evolve. The distribution of dark matter appears to have played a crucial role in shaping the structure of our universe, providing the gravitational seeds around which galaxies and galaxy clusters could form. Current space missions continue to hunt for clues about dark matter's nature. The James Webb Space Telescope peers back to the early universe, studying how the first galaxies formed under dark matter's influence. The European Space Agency's Euclid mission specifically aims to map dark matter's distribution across billions of light years, helping us understand how this invisible substance has shaped our cosmic history. The Moon is more than just a bright object in our night sky. This celestial body has orbited Earth for over 4.5 billion years, and its effects on our planet are both powerful and measurable. Every 27 days, the Moon completes a full orbit around Earth. During this time, we observe a complete cycle of lunar phases caused by our changing view of the Moon's sunlit surface. These phases progress predictably. New moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, and waning crescent. The Moon's gravitational influence creates one of nature's most reliable phenomena: ocean tides. Twice each day, the seas rise and fall as Earth rotates through two tidal bulges. These bulges form on opposite sides of Earth, one facing toward the Moon and one facing away. The ocean doesn't simply bulge on the side closest to the Moon. Instead, the Moon's gravity affects every point on Earth, with the strongest pull on the nearest side and the weakest on the farthest side, resulting in two high tides. The Sun also contributes to Earth's tides. Despite being much farther away, its massive size means it exerts significant gravitational force. When the Sun and Moon align during new and full moons, their combined gravitational forces create exceptionally high spring tides. When the Moon is at first or last quarter and forms a right angle with the Sun, we experience neap tides, when the difference between high and low tide is minimal. These tides don't align perfectly with the Moon's position overhead. Earth's rotation carries the tidal bulge forward, creating an offset of about 50 minutes. This explains why high tide occurs before the Moon reaches its highest point in the sky at any given location. The Moon maintains a unique orbital characteristic called tidal locking. It always shows the same face to Earth, a result of our planet's gravity gradually slowing the Moon's rotation until it matched its orbital period. The far side of the Moon receives the same amount of sunlight as the near side, but we never observe it from Earth's surface. Beyond creating tides, the Moon serves as Earth's stabilizer. Its gravitational pull helps maintain Earth's axial tilt at a relatively constant 23.5 degrees. Without this stabilizing effect, Earth would experience extreme climate variations that could have made the development of complex life more challenging. The gravitational relationship works both ways. Earth's considerably stronger gravitational force creates tides in the Moon's solid surface. These lunar tides cause the surface to rise and fall by 4 to 6 inches. Scientists measure these subtle changes using laser reflectors placed on the lunar surface during the Apollo missions. This orbital relationship continues to evolve. The Moon is gradually moving away from Earth at a rate of 1.5 inches per year. This recession has been ongoing since the Moon's formation, when it orbited much closer to Earth. During that early period, tides were far more extreme, potentially creating waves hundreds of feet high on Earth's ancient surface. The Moon's geology shows clear evidence of Earth's influence. Features called lobate scarps form where the lunar crust buckles under two forces: Earth's gravity and the Moon's gradual cooling and contraction. These cliff-like formations help scientists understand how Earth's gravitational pull continues to affect lunar geology. Monthly lunar phases provide a reliable natural calendar that humans have used for thousands of years. Starting from the new moon, when the unlit side faces Earth, we see a systematic progression through the phases. Each phase represents a different angle between the Sun, Moon, and Earth, revealing different portions of the illuminated lunar surface. The Moon's regular cycle has historically governed many human activities. Agricultural planting schedules, religious ceremonies, and cultural celebrations often align with specific lunar phases. Modern science has explained the mechanisms behind these phases, but their influence on human society remains significant. Recent scientific missions continue to reveal new aspects of Earth-Moon interactions. Laser-ranging experiments provide precise measurements of the Moon's distance and orbital dynamics. Seismic data from both Apollo-era and newer instruments helps us understand how Earth's gravity affects the Moon's internal structure. The relationship between Earth and Moon represents one of the most stable and well-studied orbital systems in our solar system. Understanding this relationship helps scientists better comprehend other planetary systems and provides crucial insights into Earth's geological and biological evolution. Look up at the night sky and picture our solar system's most remarkable feature: a lineup of 8 worlds, each one utterly unique. From tiny Mercury to giant Jupiter, every planet tells part of an incredible 4.5 billion-year story of how heat, gravity, and location shaped our cosmic neighborhood. In those earliest days of our solar system, a vast cloud of gas and dust surrounded our newborn sun. This solar nebula contained mainly hydrogen and helium, the most abundant elements in the universe, plus smaller amounts of heavier elements. As this nebula spun, it flattened into a disk around the forming sun, carrying a specific amount of angular momentum that would help determine the future planet's orbits. Imagine the temperatures near that infant star reaching 2000 Kelvin, hot enough to melt nearly everything. Only the toughest materials survived here: iron, nickel, silicon, magnesium, sulfur, aluminum, and calcium. Most of these elements combined with oxygen, becoming the building blocks that would eventually form Mercury, Venus, Earth, and Mars. But venture out 3 times farther from the Sun than Earth, and you'd find a completely different environment. Here, temperatures plunged to 50 Kelvin, cold enough for water, methane, and ammonia to freeze solid. This frost line marked a fundamental divide in our solar system, creating perfect conditions for building the giants: Jupiter, Saturn, Uranus, and Neptune. The formation process itself was violent and methodical. Particles in the spinning disk attracted each other through gravity, clumping together into larger and larger pieces. These grew into 1,000-meter-wide objects called planetesimals. Through countless collisions over millions of years, around 109 significant planetesimals formed. The process didn't stop there. These planetesimals continued colliding and merging through a process called accretion. They built moon-sized objects called protoplanets. Finally, these protoplanets smashed together, birthing the worlds we know today. The inner worlds had limited building materials. Only the most resilient elements could survive as solids in the intense heat near the sun. Mercury ended up mostly iron and nickel. Venus became a pressure cooker of rock and metal. Mars grew to only half Earth's size. These rocky worlds stayed relatively small, their modest gravity unable to hold on to the lightweight gases that filled the early solar system. But out in the cold zones, something far more massive took shape. Jupiter grew so large it contains more than twice the material of all other planets combined. Its composition mirrors the Sun itself, 90% hydrogen and helium. Saturn, though slightly smaller, sports its famous rings made of ice and rock. Uranus and Neptune, the ice giants, incorporated huge amounts of frozen water, ammonia and methane into their atmospheres. Location determined more than just size and composition. The inner planets are lonely places. Mercury and Venus have no moons at all. Earth has one faithful companion, while Mars has 2 tiny satellites. But the outer planets host entire families of moons. Jupiter and Saturn each command dozens of satellites, from tiny moonlets to worlds larger than Mercury. The reason for this stark difference lies in the available materials and gravitational forces. The inner solar system simply didn't have enough solid material to create large planets with strong gravitational fields. The outer planets, forming where more materials could freeze solid, grew large enough to capture and hold onto numerous moons and even impressive ring systems. The temperature differences in the early solar system acted like a cosmic sorting machine. Near the Sun, only the densest, most heat-resistant materials could survive to form planets. Beyond the frost line, an abundance of frozen materials allowed the outer planets to grow enormous, their strong gravity pulling in huge amounts of hydrogen and helium gas. When we look at other solar systems throughout our galaxy, we often see this same pattern. Rocky worlds close to their stars, giant planets farther out. Each new discovery helps confirm our understanding of how temperature and location determine a planet's final form. The composition differences between inner and outer planets tell us something remarkable about our solar system's history. The inner planets lost most of their lightweight elements, their gravity too weak to hold onto hydrogen and helium. Meanwhile, the outer planets grew massive enough to keep these elements, preserving a record of the original solar nebula's composition. Understanding these differences helps us piece together the story of our own planet's formation. Earth and its rocky neighbors represent what remained after the solar system's lighter elements were swept away, while the giant planets show us what our cosmic neighborhood was made of in the beginning. Scientists continue to refine this story, studying how distance from the Sun, temperature variations, and available materials combined to create such diverse worlds. From Mercury's iron heart to Neptune's frozen depths, each planet preserves evidence of those crucial conditions that determined its ultimate fate in our solar system. Far above Earth's atmosphere, an invisible storm rages constantly. Our Sun releases an endless stream of particles called the solar wind, blasting through space at speeds between 250 and 500 miles per second. This isn't your average weather forecast. This is space weather, and it affects our planet in ways both beautiful and potentially destructive. The solar wind begins in the Sun's outer atmosphere, the corona, where temperatures soar to 3.5 million degrees Fahrenheit. At these extreme temperatures, the Sun's gravity can no longer hold onto its outer layers. The result? A continuous outflow of protons and electrons that carries away 1 million tons of solar material every second. This cosmic breeze doesn't blow gently. As it races through the solar system, the solar wind creates a massive bubble called the heliosphere, extending far beyond Pluto's orbit. This bubble acts as our solar system's shield, protecting us from dangerous cosmic rays that originate in deep space. Without the heliosphere, life as we know it might never have evolved. When the solar wind reaches Earth, it encounters our planet's magnetic field, creating a protective shield called the magnetosphere. Picture the magnetosphere as a vast, invisible umbrella, deflecting most of the solar wind around our planet. The interaction creates a bow shock on the sun-facing side, compressing our magnetic field while stretching it out on the night side into a long tail. But the solar wind isn't always consistent. Sometimes massive bursts of solar material called coronal mass ejections erupt from the sun's surface. These CMEs can send billions of tons of charged particles hurtling toward Earth at speeds exceeding 600 miles per second. When these particles arrive, they can trigger powerful geomagnetic storms. During these storms, particles from the solar wind spiral down Earth's magnetic field lines toward the poles. As they collide with molecules in our upper atmosphere, they create the spectacular light shows we know as auroras. The northern lights and southern lights are nature's most visible reminder that space weather is real. But space weather can do more than create light shows. Strong solar storms can disrupt satellite communications, interfere with GPS signals, and even cause power grids on Earth to fail. In February 2022, a geomagnetic storm destroyed 40 Starlink satellites worth over $50 million. The storm heated and expanded Earth's upper atmosphere, creating increased drag that pulled the satellites from orbit. Scientists track solar wind using a fleet of spacecraft called the Heliophysics System Observatory. These missions work together like a single observatory, studying different aspects of the sun's behavior. The Parker Solar Probe ventures closer to the sun than any spacecraft before, while SOHO and STEREO monitor solar activity from different vantage points. The solar wind carries more than just particles. It drags along pieces of the sun's magnetic field, creating a complex web of magnetic forces throughout the solar system. When these magnetic fields interact with Earth's own magnetic field, they can create temporary disruptions that affect everything from radio communications to migratory animals. Our planet's magnetic field provides crucial protection from these space weather effects. Like an enormous bar magnet, Earth's field is generated by the movement of liquid iron in our planet's outer core. This magnetic shield deflects most harmful particles around Earth, though some still manage to penetrate near the poles. Scientists have identified two distinct types of solar wind, fast and slow. The fast solar wind streams out of coronal holes, cooler regions in the sun's atmosphere where magnetic field lines open into space. This wind can reach speeds of 800 kilometers per second. The slow solar wind, moving at about half that speed, originates near the sun's equator, and its source remains somewhat mysterious. The effects of space weather extend throughout our technological society. Astronauts on the International Space Station must seek shelter during intense solar storms. Airlines sometimes reroute flights away from polar regions where radiation exposure might increase. Power companies monitor space weather forecasts to protect their grids from solar-induced surges. Understanding and predicting space weather has become increasingly important as our society relies more on satellites and other vulnerable technologies. Scientists at space weather forecasting centers monitor solar activity 24 hours a day. watching for signs of solar flares, coronal mass ejections, and other events that might affect Earth. This constant stream of particles from space shapes our planet's environment in profound ways. From the compression of our magnetosphere on the day side to the formation of radiation belts that encircle Earth, space weather creates a dynamic system that scientists are still working to fully understand. Before GPS and smartphones, humans looked to the stars as nature's own navigation system. Among all the stars visible in the night sky, one stands uniquely still, marking a fixed point around which all other stars appear to rotate. This is Polaris, the North Star, positioned almost directly above Earth's North Pole. Finding Polaris is your key to celestial navigation, and nature provides a reliable pointer system. The most famous of these pointers is the Big Dipper, known in some countries as the plow or the saucepan. This group of 7 bright stars forms one of the most recognizable patterns in the northern sky. While the Big Dipper appears to wheel around Polaris throughout the night, it always points the way to our celestial beacon. To locate Polaris, first find the 2 stars that form the outer edge of the Big Dipper's bowl. These are called the pointer stars. Follow an imaginary line through these stars upward, away from the bowl's open end. Measuring 5 times the distance between the pointer stars along this line leads your eye directly to Polaris. It's not the brightest star in the sky, but it's notably brighter than its immediate neighbors. The Big Dipper makes a complete counterclockwise rotation around Polaris every 24 hours. Sometimes it stands on its handle, sometimes it balances upside down, but the pointer stars maintain their faithful aim toward Polaris. This constant relationship makes the Big Dipper an invaluable tool for nighttime navigation. Another constellation helps confirm your identification of Polaris. Cassiopeia, shaped like a letter W or M, depending on its position, always sits opposite the Big Dipper across Polaris. When the Big Dipper is low on the horizon, Cassiopeia rides high, and vice versa. This celestial seesaw provides a backup method for finding north when part of the sky is obscured. Polaris offers more than just direction. Its height above the horizon equals your latitude on Earth. At the North Pole, Polaris appears directly overhead at 90 degrees. At the equator, it sits right on the horizon at 0 degrees. For a quick estimate, an outstretched fist at arm's length measures roughly 10 degrees of sky. Count your fists from the horizon to Polaris, multiply by 10, and you have your approximate latitude. Other constellations serve as reliable celestial guides. Orion, the hunter, rises in the east and sets in the west. The 3 bright stars forming Orion's belt provide particularly precise direction finding. The first of these stars to rise and set, called Mintaka, marks true east and west within 1 degree of accuracy from anywhere on Earth. The celestial sphere appears to rotate around Earth once every 24 hours, but this is actually an illusion created by Earth's own rotation. As our planet spins from west to east, the stars appear to move west, just as the ground appears to move backward when you look out a train window. While most stars shift position throughout the night, Polaris appears nearly stationary because it sits almost directly above Earth's North Pole. The star's position less than 1 degree from the North Celestial Pole makes it an excellent marker for true north. Any slight circular motion it makes is too small to notice without precise instruments. Throughout human history, This celestial arrangement has guided travelers across continents and oceans. Ancient Polynesian navigators combined their knowledge of the stars with observations of ocean swells, wind patterns, and wildlife to cross vast stretches of the Pacific. The Vikings used the North Star to navigate their longships across the North Atlantic. The relationship between these celestial patterns and Earth's geography remains constant year after year. The Big Dipper's bowl will always point to Polaris. Orion's belt will always rise in the east. This reliability made celestial navigation the primary method for determining position at sea until the advent of modern electronic navigation systems. Even in our age of satellites and digital maps, knowing how to navigate by the stars provides a fundamental connection to Earth's place in space. It reminds us that we live on a spinning planet, with the stars appearing to wheel overhead as we rotate beneath them. The same stars that guided ancient mariners and explorers still shine overhead, offering their light as beacons for anyone who learns to read their patterns. The ability to find direction using the stars requires nothing more than clear skies and basic knowledge of these celestial patterns. Unlike electronic devices, stars never need batteries, never lose signal, and are visible from anywhere on Earth on a clear night. They provide a universal navigation system that has served humanity for thousands of years and continues to function exactly as it always has.